Let us say I have a magical balloon, and within that balloon I have blown the charge, not the air. So the charge will be deposited throughout the volume of the balloon. It will be distributed throughout the volume with, let us say, a charge density, which is a function, certain kind of function which is already known to us. Now, if I want to find the total charge that is contained by this balloon, then I will be needing an integration which would cover all the volume of the balloon. My dear, I will be needing the volume integration. This is the last integration in our series. We have seen line integrations, we have seen surface integrations. Now, let us understand what do we mean by the volume integration. First of all, let me tell you how to represent any volume in the electromagnetics. How to represent the volume. What is the equation of the volume looks like? But before that, can you remember what we have seen about the representation of lines and surfaces in previous lectures? My dear, if you remember, for the line we have seen that out of 3 coordinates, for the line we had 2 coordinates constant. Only one was variable. Am I right? If line is parallel to x-axis, then we had y and z constant. X is variable within certain limits. Similarly, recall for the surface. We have seen for the surface that out of 3 coordinates for the surface, we had one coordinate constant. Rest 2 are variables. The representation of the surfaces that we have seen in previous lectures was similar to this, isn't it? This is x equal to 4 surface. As we have seen, it is parallel to yz plane present at x equal to 4. It is extending from -2 to 4 in y direction. It is extending from -4 to 6 in z direction. So this is how the equation of surface was look like, isn't it? Now we are talking about the volume over here. My dear, how any volume is formed? How do we get the volume? The general formula you must be knowing. It is very simple. Length into breadth into height. Am I right? To get the volume, you should have all 3 dimensions. In other words, to get the volume, we should have all 3 coordinates are variables. No coordinate can be constant. For example, if I want to form the volume in Cartesian coordinate system, let us assume the Cartesian coordinate system. So how can I get the volume into it? It is very simple. If I want the volume, I have to take all 3 dimensions. That means I have to take the length along x and length along y, and at the same time the length along z. My volume will be formed by three lengths. For example, you can see from the figure, let us say x is changing from 1 to 2, that is length along x. Y is changing from 2 to 4, that is length along y. And z is changing from 3 to 6, that is length along z. So my dear, our volume will look like this. So what I am trying to convince you, we have seen in line integration, the equation of line is one coordinate variable. We have seen surface integration, the equation of surface is two coordinates variable. And now in the volume integration, we will have all 3 coordinates are variable and our volume will look like this. This is our case of example. The limits can be variables according to questions. But for the volume, all 3 coordinates must be variables within certain limits. And similar would be the case with cylindrical coordinates. Their rho, phi and z will be variables. And in spherical, r, theta and phi all will be variables. So for the volume, all 3 coordinates are variables within certain range. Now let us discuss about the differential volume dV. Now my dear, you are very much familiar with the method of integration. We have seen line integration, surface integration. Actually in any kind of integration, we actually have 2 steps. In very first step, what we do, in very first step, we find the infinitesimal value of the function, a very small value of the required function, by considering the very small or infinitesimal or differential part, isn't it? If it is a line integration, then we consider a very small length, infinitesimal length, or differential length, dl. If it was the surface integration, then we take the differential surface, a very small surface. Similarly, here in volume integration, we are integrating over the volume. So in first step, we will take an infinitesimal value, a differential volume from the given volume, that will be our dV. And as we have seen, in the second step, we will cover the entire volume by taking proper limits of the integration, isn't it? So let us write the dV, the differential volume, the infinitesimal volume for the Cartesian coordinates. Now, my dear, in the very beginning of the lecture, I have told you that for getting the volume, we need all three dimensions. We need multiplication of all three lengths, isn't it? So if I want the volume, the infinitesimal volume, the differential volume in the Cartesian coordinates, then I would be needing the infinitesimal length, the differential length along x-axis, also the infinitesimal length, the differential length along y-axis, say dy, and the infinitesimal length along z-axis, that is dz. And my small volume, my differential volume, will be product of all these lengths, and hence the differential volume will be dx, dy, dz. Similarly, if we consider the cylindrical coordinates, we know that the variables are rho, phi and z. We also know that the differential lengths are d rho, rho d phi and dz. You must be remembering that the differential length for phi is rho d phi, isn't it? This much details we have seen in the lectures of coordinate systems. So the differential volume for the cylindrical coordinates would be multiplication of all these three lengths, that is d rho, rho d phi and dz. And similarly, we can say that the differential volume for spherical coordinates will be the multiplication of all three differential lengths, that are differential length for r, differential length for theta and differential length for phi, and the dv you can see from the screen. But my dear, just remember the shorthand technique from the lecture of surface integration. How did we write the differential surface ds from the expression of differential length dl? Do you remember? On the similar lines, we are not going to remember dv as if, but we will write the differential volume dv from the expression of differential length. That is, we are going to write dv from the expression of dl. So once again, consider the Cartesian coordinate system. You know the differential length dl for Cartesian coordinate system is like this. My dear, you have to remember the expressions of dl for each coordinates very carefully. So this is dl for Cartesian. Now to write the dv, differential volume, from this dl, just skip the unit vectors and multiply all the coefficients. So my dear, we get the dv. The dv will be, the differential volume will be dx, dy into dz. Similarly, consider the cylindrical coordinates. You know the dl for cylindrical coordinates is like this. Once again, skip the unit vectors, multiply all the coefficients, and our dv will be rho d phi dz. Isn't this very simple? Let us do one more time. Consider the spherical dl. Once again, skip the unit vectors, multiply all the coefficients, and the differential volume or dv for the spherical coordinates will be, as you can see, r square sine theta dr, d theta, d phi. Isn't this very simple? You know, it is quite logical to do like this, because what is the volume? It is the multiplication of all three-dimensional lengths, isn't it? One more thing we can notice over here: the dv, differential volume or volume, by its nature is a scalar quantity, and hence you must have observed that we didn't write any unit vector in the expression of dv. The dv is a scalar quantity. One more thing, generally we take volume integration of the scalar functions, scalar fields. We can also take the volume integration of vector fields also, but that we will see in the advanced topics. But as if now you can remember like this: volume integration are generally taken for the scalar fields. So dv or differential volume is a scalar quantity. We have seen the line integrations. Over there we have seen dl, differential length, that was a vector quantity. We have seen the surface integration. Over there we have seen differential surface ds, that was also the vector quantity. Of course dl and ds both can be used as the scalar ones, but that is different story. But by nature dl and ds are the vector quantities, while differential volume dv is a scalar quantity.